Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Titled on our agenda, Implementation of a Non-Strict Functional Language on Rotor. You can see it has an alternate title here on the slide deck here. It'll be presented by Oliver Hunt. The work is done by Oliver and Nigel Perry of the University of Canterbury in New Zealand. Nigel is a New Zealand computer scientist whose research interests range across many aspects of programming languages, from implementation type systems to paradigms, virtual machine environments, their design and impact on computing. Since 2000, Nigel has been involved in various projects related to .NET, from the implementation of languages to convening the C# Standards Committee and advisory role with Microsoft. His ongoing research interest is on how different language paradigms can be supported on the CLI, or how the CLI might need to be developed to support them. Oliver is a master's student at the University of Canterbury, where Nigel is a senior fellow. His research centers on the implementation of Haskell and the CLI, and clearly an interest in implementing compilers for non-strict functional languages. He also has interests in image and graphic processing, and also was responsible for porting the Rotor gyro patch to the Mac OS implementation of Rotor running on PowerPC. So I'd like to introduce Oliver up here to give this talk.
Alrighty, hi. Today I'm going to be talking to you about the work that Nigel and I have been doing over the last few months, which has more or less been around the idea of avoiding doing any work on the .NET platform. Today's talk, I'll be giving you a basic rundown of what we've been doing, why we're doing it, covering some of the background information of this field. After that, I'll just do a brief coverage of things that people have done in the past, what previous attempts have been made to get functional languages to run on type virtual machines like .NET, and what approaches have been taken. Then we'll start looking at the challenges and the problems that people encounter when we try and undertake these projects. Finally, we'll give a rundown of what we've actually accomplished so far, results, basic timing information for efficiency, even a small demo. Then we'll just talk about what possible directions of research that our research has actually opened up, what we'll be able to do in the future, and what will lead on from this. And finally, there'll be a small amount of time at the end for you to ask me questions. Right. So what are we doing? We are trying to compile the Haskell 98 specification with no modifications of any kind, so that it will run directly on .NET in native IL. Now, Haskell, for those of you who aren't aware, is one of the world's most popular functional programming languages. And there are actually a number of problems associated with implementing it on a platform like .NET. The big ones are, can we actually do it reasonably? Is it going to actually be too slow to be usable? And would there be changes to the IL that we could make that would further improve its performance without having too much of an impact on the virtual machine itself? For those of you who don't know that much about Haskell, or have never heard of Haskell before in your life, Haskell is actually well known. It's one of the premier functional languages in use today. It's used widely in academia and industry. Amongst its many features, it's got a very, very firm belief in non-strict evaluation. And the primary compiler that people use for Haskell is the Glasgow Haskell compiler. There are a number of others, but GHC is the lion's share of them. Now, GHC provides, from the point of view of being useful to us, GHC actually provides an intermediate level output that's sole purpose is to allow people to write backends, which is convenient because that's what we're trying to do. This means we're not compiling Haskell per se, we're compiling core, which is a slightly reduced subset of Haskell with awful syntax. Also, at this stage, GHC has already done all the type inference for us, which removed that very mechanical task and thus saves us time and lets us actually work on how to make it go. GHC also provides a number of extensions to the Haskell 98 specification, which provides further directions of research in this form of implementation. Some of them we're actually going to need to implement to get this backend running in the first place, but we'll discuss that later. This brings in the question of why we're wanting to compile Haskell to .NET, and well, it basically comes down to different languages are suitable for different tasks. For instance, an assembly language is very, very good for writing a bootloader. You wouldn't want to write anything else in one. On a more abstract level, functional languages tend to deal with processing lists a lot better than an imperative language, and imperative languages tend to perform much better if you're trying to write event-driven code like a GUI. What we're doing here is we're adding the existence of a non-strict functional language to the toolbox of programming languages that are available to a person programming on the .NET virtual machine. Our other reason for doing this is to see whether we can. .NET is meant to be language agnostic. However, most of the languages you see compiling to .NET are strict imperative and object-oriented languages, which are more or less the same. C#, Visual Basic, Java are all different spellings of the same programming language. So we're going to be seeing whether this is actually possible. Okay, there have been a number of different attempts in the past to get functional languages to run on typed virtual machines. Of these, there are two real approaches. The first approach people use is a bridge. A bridge, in this case, is more or less a small software API that allows the virtual machine to communicate with the functional language, or vice versa. What this means is that the functional language loses many of the advantages that the virtual machine provides, such as any security features that might be provided, or the cross-platform portability, as the functional language itself will still be running on the native machine. Prior examples of work that have done this are things like the Lambda Haskell implementation for Java, which used the JNI, and Hugs.NET, which used just the generic ability of .NET to talk to external processors. The other approach taken by people trying to do this sort of work is to create a new language. Now, this isn't necessarily creation of a new language directly from scratch. You can take a standard functional language and remove some of the features, such as non-strictness or more obscure features that I can't think of right now. There's also the possibility of doing a mixed compiled and interpretive approach. This is where we start using things like reflection to do runtime type generation and type inference. And the other approach that can be taken is to take a inconsistent type system and convert it to an object-oriented type system. This approach was taken by F#, for instance. Other examples of previous work that have taken this approach includes Pizza, which was a strict functional language for the JVM, and the Mondrian language, which used a mixed and used an interpretive and reflection type approach to generating the required type information. Right. Now, getting the Haskell 98 specification to run on the .NET platform has a number of challenges. The four I'll be going over in detail today include non-strict evaluation, using functions as values, partial valuation, and type switches. Of all of these, non-strict evaluation and partial evaluation are likely to be the only ones that are new to most people. However, I'll describe them in more detail later on. Right. Non-strict evaluation is a mechanism by which we delay any form of evaluation of expressions until we actually need the result. Haskell lives on this. It does it everywhere. This allows Haskell to do a number of things that you can't do in strict languages, amongst others. These include infinitely large lists. You can have expressions where you divide by 0, but if you never actually try and access the values that you've divided by 0, you don't have an error occur. Or because until you try and get that result, it will never be evaluated. Previous approaches to getting non-strict evaluation to work include external non-strictness, such as used by the Mondrian system. This is where the developer himself or herself is required to actually manually evaluate each method. So this means you've got added burden to the developer, and the developer actually needs to be aware of when and where they need to perform evaluation explicitly. Another approach, which was introduced by Nigel Perry late last year, was the concept of a JIT object. Broadly speaking, a JIT object is similar to the proxy pattern for those people who like software patterns. This is where the non-strictness is hidden by the client behind a object or a subclass of an object. This means that effectively any method that you might be calling on this or any way of accessing the value will be wrapped up behind a function call of some kind, and that function call will do explicit evaluation through a delegate or some such. Unfortunately, JIT objects, whilst they have many advantages, don't support disjoint union types very well, and disjoint unions are very, very common in the Haskell programming language. They are its basic data type. The approach we've taken is to use internal non-strictness. That is similar to what JIT objects are doing. This provides the best interoperability with other languages, and it means that the software developer doesn't need to know anything about what's going on in the background. Now, for primitive types, we have used more or less the JIT object structures because primitive types only have one possible alternative. They're not a disjoint union, there's only one possible value, and for that reason, JIT objects will still work. For reasons of efficiency, we have optimized this down to using just a single class, a single parametric class, which can perform the evaluation as and when necessary. For reasons of interoperability, again, we've added implicit cast operators, a C# feature, so that the developer, once again, doesn't need to know that they're dealing with anything other than a primitive type, as C# or whatever language they're using will do the cast for them implicitly. Function types are another problem that we'll go into in a brief period, because in Haskell you can create a new function on the fly which may not necessarily need to be evaluated. Now, for disjoint unions, we have to deal with each alternative and the basic data type. For this, we've created an abstract class to describe the data type itself, and use subclasses of that class for each possible alternative. Furthermore, for discrimination between each type, we've added a tag field. We'll get into why we've done this in a little while. Unfortunately, the way we've approached it means that you cannot safely just do a straight cast, because the implicit or the explicit casting operators of C# are not part of the .NET type system itself. For this reason, we've added asx methods, which look fairly similar to the as style operator of C#, and thus make it slightly nice to work with. To get non-strictness going, we have added an extra subclass, a thunk, which has the sole purpose of wrapping up each function call to contain a call to the evaluator followed by the actual return type if necessary. As I've already said, casting doesn't work, and because of the way it's implemented, it's not entirely transparent. However, most of that is caused by the fact that disjoint unions aren't really something you get in OO languages anyway, so it's kind of an arguably okay thing to have. As a basic example of what actually happens internally, we can take the basic recursive list structure of Haskell, which in this case we're defining a list of type A, which has two subtypes, or two alternatives, a cons, which consists of two fields, an A and a list of A, and nil, effectively the empty list. As we can see, this generates one abstract class list, which has just a couple of fields, and then three subtypes. In the thunk class, you can see the generator function. Now, in that case, the as cons and as nil methods actually will call the generator function and then stores the result of that generator. Right. The next problem appears fairly trivial at first glance. Functions as values are effectively a function pointer. Now, .NET actually provides function pointers in the form of delegates, which are referred to generally as object-oriented function pointers. Unfortunately, the implementation was relatively inefficient given the fact that they are used everywhere in Haskell. And also, as I mentioned earlier, it's difficult to combine them with non-strictness, as we can end up generating a function that may not necessarily be evaluated at any point. So what we've done is we have replaced this using a parametric function type. We have an invoke method, so it loses some of that transparency. However, once again, for reasons of interoperability, we have provided implicit conversions to and from the basic CLI delegate types. later on I'll get into describing exactly why and how we've extended it to support partial application. We also need to support it later on to support higher rank types. Higher rank type is effectively a pointer to a function that has a generic argument, but to which we haven't yet applied the generic argument. Partial evaluation is the calling of a function without all of the argument that that function might originally have taken. In a very simple case, we can define a function inc, which has a single argument x, and we then call the function plus with x applied. Now, plus is actually in Haskell a function of 2 arguments. So in this case, if you call inc3, the result will actually be a function that adds 3 to any function, to any value you then pass to it. To do this, we then extend the function type we previously created so that you can store instant variables with each given function. Now, the last of the big problems is the existence of type switches. Now, type switches in .NET are very, very slow because they effectively require a series of casts to each class, and because they take into account subtyping information, that can actually be quite expensive. Now, for Haskell, what we actually need to do is a strict type comparison. So for this reason, we now use that tag field that we originally added to each of the disjoint union types. This means it's a lot faster to actually perform the operation, and it unfortunately effectively duplicates the hidden virtual machine tag, so there's a V table for each class instance. For that reason, to avoid any memory overhead, we've actually made the tag property become a virtual method. So actually evaluating it still requires a method call, but it's nonetheless still faster than a full type lookup. In its current status, the compiler is functional. It's unfortunately still incomplete. It's got most of the Haskell language supported at the moment. However, it's not yet got the full set of the Haskell 98 libraries completed. Big problems at the moment include the fact that GHC's internal representation unfortunately includes extensions to the Haskell specification, such as higher rank and higher kinded types, which we have not yet dealt with. And these influence what we can and cannot yet compile. As far as performance goes, the generic prime civ program that people tend to use, we can calculate the first 1,000 primes in under twice the time that Glasgow running the GHC compiler running natively can do it in. Unfortunately, as time goes by, that gap tends to increase relative to each other. Now, as I've already pointed out, higher rank and higher kind types cause us problems. Now, as higher rank types are those function pointers to functions which have unapplied type values, type arguments applied, we have a kind of solution that works in some of the cases at the moment, however, still has problems associated with it. And higher kinded types are types where you can end up actually having a type applying types to your type arguments. As yet, we haven't yet worked out how we can do this reasonably, that is, without using reflection. Currently, we bypass this, and the most trivial case, I/O, tends to require it quite frequently. However, we've hardwired it all straight to the .NET I/O subsystem, which means that we can get a reasonable degree of functionality at the moment. Compared to native implementation, we have huge numbers of classes. For instance, some of the base libraries can produce upwards of 500 or 600 classes when there are below 100 methods to begin with, but most of this is due to having to provide extra functions and delegates to handle the actual non-strict evaluation. So once we've actually got this implemented and running reasonably, we'll start looking at what modifications to IR we can do that would actually improve the performance overall. And just to demonstrate that I am actually telling the truth, we have a demonstration. Useless. And I can't get it. Tab. Virtual PC, no. Virtual, yeah. Excellent. Right. Oh. Hello? This is byte. And apparent. There we go. Right, live. In this case, we've just got maximize. Oh, this is irritating. And that's just not cooperating anymore. Now we go Alt Enter. Virtual PC console. Now, right. Given it's not actually working full screen mode. Yep. And it looks like the virtual PC is now crashed. Oh. In fact, the laptop has crashed. And unfortunately, that's a problem with live demonstrations. If people want to have a look later, they can come around and have a look. Is it alive? No, it's not. It's walking off. That may come to life while I still have time. Does anyone have any questions? No. Any questions at all? No one? Oh.
Has there been other work in implementing closures on .NET? I'm sure I've read something about that somewhere, which sounds similar to...
Yeah, I have heard of it, but I didn't manage to find any papers on it when I was originally doing any research. Of course, when it comes time to actually do the writing that I've been avoiding for the last few months, I'll have to do some more significant research on that.
Is it available now, or what do you anticipate?
It should actually be to the level where you'll be able to download in the next few months or so. It still has significant issues. Occasionally, it will lose touch. This is on blaming the laptop. This isn't mine. That I'm fairly sure it's just a laptop because I haven't actually started the compiler yet, so I can't blame it. It has a few bugs at the moment. Every now and then it will lose type variables, but I'm fairly sure that's just one particular case, and I just haven't had time to look into that particular bug yet. The big problem from the point of view of getting it usable is that GHC has compiled monads such that they use higher rank types, and we haven't yet worked out how to implement them nicely. And once we get those going, we can get the monadic I/O going properly, which means most functions, most programs that you can write should actually run. Right. That answers the question. No? Any other questions? No? In that case, I'll leave it to John.